Your Java application is under a massive traffic spike.
Oh, the classic nightmare scenario.
Right. And you assume your thread pool is, I don't know, spinning up hundreds of workers to save you.
Yeah.
But it isn't.
Nope, not at all.
It's actually just stacking tasks in a queue until the entire system completely runs out of heap memory and dies catastrophically.
Just a cascading failure.
Exactly. So, welcome to the deep dive. Our mission today for you, the listener, is untangling the wildly misunderstood mechanics of Java thread pools in production environments.
It is a topic that trips up so many developers.
It really does. And today, we are pulling insights from technical documentation on thread pool executors, the new Java virtual threads paradigm, and a really fantastic architecture piece titled Code Under Load.
Some great source material for this one.
Yeah. So, okay, let's unpack this, because if a thread pool isn't just like a performance button or a magic box that creates threads on demand to go faster, what actually is the mechanism here?
Well, at its core, a thread pool is a mechanism for controlling how much work executes concurrently.
Like a control valve.
Exactly like a control valve. And we really have to establish this fundamental distinction right away.
Okay, lay it on us.
If you submit 1,000 tasks to a pool that has, say, 10 workers, that does not mean Java needs or even wants to create 1,000 threads.
Which, I mean, that runs completely counter to the whole developer instinct, right? Like, more resources equal more speed?
Right. The immediate assumption is usually, well, if we just spawn a thread for every single request, the application will just plow through the backlog.
Yeah, just brute force it.
Exactly. But to understand the flaw in that instinct, we have to look at the underlying operating system problem that thread pools actually solve.
Because threads aren't free.
They are incredibly expensive resources. Each native Java thread consumes about 1 megabyte of memory just for its stack.
Oh, wow.
Yeah. So if you take that naive approach of creating a new thread for, say, 10,000 concurrent requests...
You're immediately consuming 10 gigabytes of RAM.
Right, just on thread overhead.
Yeah.
Before you even process a single byte of actual business logic.
That is wild. And, you know, even if you have the RAM, you're going to hit the CPU scheduling wall eventually, right?
Oh, absolutely. Because a CPU can only execute one thread per core at any given microsecond.
Right.
So if you have an 8-core processor trying to juggle 10,000 active threads, the OS scheduler enters the state of just complete thrashing.
Meaning it spends more time managing the threads than running the code.
Exactly. It spends all its CPU cycles pausing threads, saving their execution state, doing context switching, loading the next thread into the L1 cache.
Wow.
It spends more time doing all of that than it spends actually executing your application code. The system effectively grinds to a halt through its own internal friction.
So it's literally choking on itself.
Yeah. And so the Java Executor framework steps in to solve this exact problem by decoupling the act of submitting work from the actual execution of that work. It imposes boundaries.
Okay, I want to use an analogy here to make this relatable. Think of like a really busy restaurant kitchen.
I love food analogies. Let's go.
Right. So the incoming customer orders are your tasks, and the cooks in the kitchen are your threads.
Okay, tracking so far.
If you suddenly get 1,000 orders on a super busy Friday night, you don't instantly hire 1,000 cooks and shove them into a commercial kitchen designed for 5 people.
Right. The cooks would just be bumping into each other, fighting over the same stoves.
Stealing each other's cutting boards.
Yeah, nothing would get cooked. The overhead of managing the space totally destroys the throughput.
Exactly. So instead, the restaurant operates with a fixed number of cooks, the workers. And there's a ticket rail where the incoming orders wait, which is your queue.
Right.
The cooks simply pull orders from the ticket rail as fast as they can, one by one. And this restaurant kitchen model translates directly to the internal anatomy of a Java thread pool executor.
It really does. The core capacity of the kitchen, the maximum occupancy, the length of that ticket rail, they all perfectly correspond to configuration parameters.
Like core pool size, maximum pool size, and work queues.
Precisely. And the most fundamental of those is the core pool size. This is your pool's normal worker capacity, basically your regular shift of cooks.
Right, the base team.
Exactly. If tasks arrive and you have fewer than the core number of workers currently running, the executor will always prioritize creating new workers to handle them.
So if your core pool size is 2 and 2 tasks arrive, the executor spins up 2 OS threads to process them immediately.
Yep, no waiter.
But, and this is where I think things get tricky, let's look at what happens when the traffic spikes.
Yeah.
Because this is where the most common developer misconception lies regarding how thread pools scale under load.
Oh, for sure. This is the big one.
So let's run a specific simulation from the sources. We're going to configure a pool. We set the core pool size to 2. We set the maximum pool size to 5.
Okay.
And we give it a bounded queue capacity of 3. So 2 core workers up to 5 max workers and a waiting line that holds 3 tasks.
That is a very standard, constrained environment for testing saturation.
Right. So tasks 1 and 2 arrive. As we just established, our 2 core workers spin up and handle them immediately.
The core is now completely full.
Exactly. But the traffic is still accelerating. Task 3 hits the system. Both core workers are busy. So what did this all mean for task 3? Does the pool immediately look at that maximum pool size of 5 and say, hey, we have headroom, let's spin up a 3rd worker?
Nope. And this is the twist that catches everyone off guard. The JVM actually prefers to queue the task instead.
Wait, really? It just lets it sit there?
Yeah, the system is aggressively optimized to avoid creating new threads if it doesn't strictly have to.
Because they're so expensive.
Exactly. With a standard queuing ThreadPoolExecutor, once that core size is reached, the executor prioritizes placing incoming work into the queue over interacting with the operating system to allocate a new thread.
So it's doing the math.
Right. It calculates that letting a task wait a few milliseconds for a running thread to finish is far, far more efficient than incurring the massive system call cost of spinning up a brand new OS thread.
Okay, so task 3 goes into the queue.
Right.
Task 4 arrives. It sits in the queue too. Task 5 arrives. It fills the very last spot in our queue capacity of 3.
Yep.
And our 2 core workers are still furiously churning through tasks 1 and 2. Then task 6 arrives at the door.
Now we have a problem.
Right. We have 2 core workers busy, a queue of 3 completely saturated, and a max pool size of 5.
And this is the exact moment the executor is finally forced to scale up.
Only now.
Only now. When the queue is entirely saturated and has physically rejected the new element, does the executor evaluate the maximum pool size? It realizes, okay, the waiting room is full, but the building still has maximum occupancy limits we haven't hit yet. So it finally allocates that expensive new OS thread.
And task 6 executes on this newly created 3rd worker.
Exactly.
So then task 7 arrives, we get a 4th worker. Task 8 arrives, we get a 5th worker. And now we've actually hit our maximum pool size of 5.
Yep. Every single piece of capacity we configured is fully utilized.
That is wild. I mean, that sequence completely highlights why maximum pool size functions as a ceiling of last resort, not some immediate trigger.
Exactly. It's an emergency valve. It only opens when the queue fails to absorb the mismatch between tasks arriving and tasks being processed.
Which makes the queue itself the actual primary control mechanism for thread creation.
It does. And the sources specifically warn that developers often misconfigure this by using an unbounded queue.
Right, an unbounded queue. So a queue backed by like a linked node structure that can hold essentially an infinite number of tasks.
Yeah, and if your queue is unbounded, it mathematically can never fill up.
Oh, I see where this is going.
Right. If the queue never fills up, the executor will never hit that trigger condition to create threads beyond the core pool size.
Wow.
You could confidently set your maximum pool size to 1,000 in your configuration, but if you pair it with an unbounded queue and a core size of 2, your application will literally only ever run 2 threads.
And the tasks will just pile up in system memory endlessly.
It's endless.
Just millions of incoming orders hanging on an infinitely long ticket rail while 2 cooks sweat it out.
Until the inevitable out-of-memory error takes down the entire JVM.
That is terrifying. And that is exactly why bounded queues are so critical. But I mean, bounded systems force us to confront the reality of absolute exhaustion, right?
Yeah, we have to deal with the limits.
Going back to our simulation, we have 5 workers maxed out and a queue of 3 completely full. Then task 9 arrives.
Yeah.
The system literally has no memory allocation left for this request based on our bounds. It has to drop it.
It does. The executor invokes its RejectedExecutionHandler. It's out of space, it's out of threads, and it simply must reject the work.
And for a developer, rejection feels like a catastrophic bug. Like, we write software to process data, not drop it on the floor.
Nobody likes throwing exceptions.
Right. Throwing a rejected execution exception, which is the default abort policy in Java, usually sets off alarms.
Well, what's fascinating here is that it sounds like a failure, but it is actually a vital survival mechanism.
Backpressure, right.
Exactly, backpressure. When you configure a bounded system, you are explicitly defining how the application should degrade under extreme duress.
Because the sources mention another policy that seems pretty brilliant for this exact scenario, the call-runs policy.
Oh, that's a great one.
Right, because instead of just throwing an exception and dropping the task entirely, It forces the thread that submitted the task to execute it.
Yep.
So if Tomcat's main web server thread hands over a request and the pool is full, Tomcat has to process it itself.
Which fundamentally changes the flow of the entire system. By forcing the caller thread to do the work, you are temporarily tying up that submitting thread.
It's busy. It can't go back and accept more incoming network connections.
Exactly. And that creates natural mechanical backpressure. The OS network buffer starts to fill up, TCP window sizes shrink, and eventually the load balancer sees that this node is slowing down and routes traffic elsewhere.
It communicates exhaustion upstream organically. Because if you don't have deliberate rejection like this, and you just let an unbounded queue swallow everything, the problem isn't actually solved.
No, it's just hidden.
The queue grows silently in memory, and the user on the other end is just staring at a spinning loading wheel for 3 minutes because their request is like 50,000th in line.
And eventually the client times out anyway, they hit refresh,
Sending another request into the queue.
and the system dies in a cascading failure. Bounded queues with deliberate rejection policies fail earlier, and they fail more predictably.
Right. Turning away a few requests at the peak of a traffic spike is infinitely healthier for a production system than letting the entire application cluster catch fire and take everything down with it.
100%.
But, okay, let me play devil's advocate for a second.
Go for it.
The immediate temptation to avoid dropping those requests is just brute force, right?
Right.
If 10 threads aren't enough to handle the peak, and we have the RAM, why not just set the maximum thread pool size to 100 or 500? Just hire 500 cooks and buy a bigger kitchen.
I see this all the time. But that brute force approach completely ignores the nature of the workload itself. You have to profile whether your specific tasks are CPU-bound or I/O-bound.
Okay, let's break that down.
Thread pool sizing is fundamentally an architecture problem, not just a configuration slider you can push up.
So for context, CPU-bound tasks are actively grinding the processor. Complex algorithmic calculations, parsing massive XML documents, cryptographic hashing. The processor is physically working the entire time.
Exactly. And if you throw 500 threads at an 8-core CPU for CPU-bound tasks, you are actively destroying your throughput.
Because the processor can still only do 8 things at once.
Right. Adding more threads just exponentially increases that context switching storm we discussed earlier. The CPU spends all its time managing the threads rather than, actually parsing the XML.
Right.
For CPU-bound workloads, your thread pool size should usually be very close to the number of physical cores you actually have available.
That makes sense. But if the workload is I/O bound, meaning the application is spending the vast majority of its time just waiting for a network packet, or waiting for a database query to return, or waiting for a disk read, the CPU is basically sitting idle.
It's just twiddling its thumbs.
Right. So in that scenario, additional concurrency is necessary to keep the processor fed. While one thread is blocked waiting for the database, another thread steps in to do some processing.
And this is where developers often overcompensate. They realize the tasks are I/O bound, so they crank the maximum pool size up into the thousands.
Just massive numbers.
Yeah, and it might improve throughput up to a point, but eventually you are just shifting the pressure point.
What do you mean?
Well, if your thread pool allows 1,000 concurrent database queries, but your database connection pool is maxed out at 100 connections, 900 of those threads are just going to be blocked waiting for a connection object.
You haven't increased throughput at all. You've just created a traffic jam slightly further down the highway.
Exactly. You have to size the pool across the entire life cycle of the request.
Okay, so assuming we've sized it perfectly across the board, traffic spiked. We scaled up to, say, 500 workers, we handled the load, and now the dinner rush is over. Traffic drops to 0.
Time to close up shop.
Right. We don't want 500 idle threads permanently consuming system memory.
No, we don't. And this introduces the keep alive time configuration.
Okay.
This setting dictates how long excess idle threads, and specifically the ones created above the core pool size, how long they should wait for new work before they terminate themselves.
So if we set keep alive time to 60 seconds, and a worker thread sits around for a minute without pulling a new task from the queue, it shuts down, returning its memory to the operating system.
Yep.
So the pool naturally shrinks back toward its baseline core pool size.
Exactly. It makes the thread pool this living, breathing mechanism that breathes in during spikes and breathes out during lulls.
That adaptability is so crucial for long-running services.
It really is.
Now, that low-level understanding of core sizes, queue thresholds, and keep alive times is fascinating. But let's pivot to the reality of how we build software today. because most developers aren't instantiating raw ThreadPoolExecutor classes by hand anymore.
Oh, definitely not.
They rely heavily on frameworks like Spring Boot to manage the heavy lifting.
And Spring Boot brings incredible developer velocity, but it relies heavily on auto-configuration.
Right.
For instance, if you use the @async annotation, Spring Boot automatically configures a ThreadPool task executor under the hood.
But it's applying its own default configuration to the exact same Java concurrency rules we just mapped out.
Yes, often with disastrous defaults if you don't override them.
Okay, prepare me.
By default, Spring's auto-configured executor sets an unbounded queue capacity. It defaults to integer max value.
Are you serious?
Dead serious.
So, which means, based on the simulation we ran earlier, it will basically never scale past its core pool size under heavy load. It will just queue tasks into infinity until the JVM runs out of heat memory and crashes.
Frameworks abstract away the boilerplate, but they do not suspend the laws of physics.
That is a great way to put it.
If a developer doesn't understand that queue saturation is the trigger for thread growth, they will be completely baffled when their Spring Boot application with a max pool size of 100 refuses to spin up more than 8 threads while simultaneously crashing from out-of-memory errors.
Right. When the abstractions leak in production, you are left debugging core Java concurrency anyway.
You really are.
But, and here's where it gets really interesting, the entire Java landscape recently experienced a seismic paradigm shift regarding how we handle I/O-bound concurrency. We've been dissecting operating system threads, which are heavy, memory-intensive, and require complex pooling to manage.
Right.
For Java 21, fully integrated virtual thread.
For Project Loom, it fundamentally changes the entire cost equation.
How so?
Virtual threads are managed entirely by the Java virtual machine. They are not mapped one-to-one with native OS threads.
Okay.
They are incredibly lightweight, consuming kilobytes of memory instead of megabytes.
And the documentation notes that Java now provides executors new virtual thread per cask executor. And the architecture of this executor is wildly different, right? It doesn't have a core size.
Yep.
It doesn't have a maximum size. It doesn't even have a queue. It simply starts a brand new virtual thread for every single submitted task, regardless of how many there are.
Yep. Just spins one up.
So if 10,000 requests come in, it immediately spins up 10,000 virtual threads. So does this mean the era of thread pools is just over?
Yeah.
Did Java finally give us the magic performance button that just scales infinitely?
It is highly tempting to view it that way, but we really have to apply a serious reality check here.
Okay, burst my bubble.
Virtual threads solve the local resource exhaustion problem. They make it practically free to have a thread sitting around waiting for a network response. They prevent your JVM from running out of thread memory.
So the JVM is perfectly happy managing 100,000 virtual threads blocked on an external API call.
The JVM is happy, but what about the external API? Virtual threads do not remove bottlenecks. They bypass the local thread bottleneck only to expose the next physical constraint in your architecture significantly faster.
Wow. Because if I spin up 10,000 virtual threads to write data to a PostgreSQL database, and that database is configured to only accept 200 concurrent connections, the virtual threads haven't solved anything.
Exactly. You haven't magically created a 10,000 connection database. You have simply generated 10,000 concurrent pieces of work that are all going to instantly bottleneck at your connection pool.
Right.
The bottleneck just moved from the JVM's thread scheduler to the Hikari CP connection pool, or to the database's CPU, or even to the network interface card.
It's the ultimate double-edged sword. You've basically removed the brake pedal from your application server, which means you are now driving into the downstream bottlenecks at Mach 2.
Precisely. It forces you to look at the entire system architecture, not just the code block right in front of you.
That is so true. So, to synthesize everything we've unpacked from our sources today for you, the listener, a thread pool is not a magic performance button. It is a highly controlled pipeline.
Absolutely.
It is intentionally designed to absorb the mismatch between how fast tasks arrive and how fast your system can actually process them. It dictates how concurrency scales, and most importantly, it acts as boundary that defines exactly what happens when your system's capacity is totally exhausted.
The most valuable mental framework you can take away is to stop focusing purely on the thread count.
Right.
Next time you encounter a new fixed thread pool or you rely on a framework like Spring Boot, ask the structural questions. Where do these tasks actually wait? What is the physical limit of the queue?
How much work should actually execute concurrently based on whether the tasks are grinding the CPU or waiting on I/O?
Exactly. What is the explicit rejection behavior when we hit absolute capacity?
And finally, if we do scale up, what is the next downstream dependency that it's going to break?
Always ask that.
Which brings me to a final thought I want to leave you with, building right off that warning about Java virtual threads. If these ultra-lightweight virtual threads allow your Java application to effortlessly spin up tens of thousands of concurrent tasks without crashing the JVM, does your shiny, newly upgraded virtual thread architecture actually pose a massive self-inflicted DDoS threat to your own internal databases and legacy downstream APIs?
Oh, that is a scary thought.
Right. Just because your application server can suddenly handle 50,000 concurrent requests doesn't mean your legacy infrastructure can survive the impact. Something to deeply consider the next time you decide to casually upgrade to Java 21 and just flip that switch.
It really is a profound shift in where the pressure points in a system live. The friction doesn't disappear, it just relocates.
It really does. So the next time your system is buckling under load, remember the restaurant kitchen. Don't just blindly hire more cooks. Take a hard look at the ticket rail, figure out exactly what happens when that rail is full, and whatever you do. Don't let the entire kitchen catch fire just because you were afraid to deliberately turn away a single order. Thanks for joining us on this deep dive.